Okay, continuing the discussion. Question 14. Consider two waves shown in this figure. Each wave can be thought of superposition of two sound waves with slightly different frequencies, meaning what we're seeing is beats, an increase and decrease in amplitude. In which of the waves, so A or B, are the two component frequencies farther apart? So, are the frequencies farther apart? So more change between them or less change between them. So for example, if we were to listen to 440 hertz, which we have done, and 442 hertz, the difference in these is 2 hertz, so we would hear a beat frequency of 2 hertz. I'm going to write that over here, beat frequency of 2 hertz. So you subtract the two frequencies, meaning you'd hear 2 wah-wah-wahs per second. Alright, so if we investigate, we could take a look. Here's 0.2 seconds and 0.2 seconds. So we see 1, 2, 3, and a little more waves. So 3 plus wavelengths here. And we see 1, and then maybe about a half, so about 1.5 wavelengths here. So if you're listening, you're going to hear more waves per time up here than you are down here. So if you hear more waves per time, it means the beat frequency is higher, therefore the difference between the two is greater. So we would hear a greater, or the two component frequencies would be farther apart for this situation because we hear a higher beat frequency. Meaning instead of the difference between 440 and 442, it would be something like 440 and 446, just for example. Alright, 15. Is there a Doppler shift if the source and the observer move in the same direction with the same velocity? Explain. So the answer is no. And let's say you have two cars, and this car is laying on the horn, right? And you're over here listening. Here's your ear. So, yes, because this car is moving to the right, the waves are going to be compressed, but if the distance between you and the source of sound doesn't change, the number of waves that leave this car per time is going to be the same as the number of waves that get here per time. You would see, when you're watching these sound waves, you wouldn't be able to really see them, but when you're watching these sound waves, the velocity with respect to you would be less than 343 meters per second, but you'd see this compressed wavelength, so you'd see a reduced speed, a reduced wavelength, but the frequency would be the same. So no, you would not. If you were to look at the formula, if the velocity of the source of sound and the listener are the same, the frequency is going to be the same as well. 17. So the figure shows a child is swinging and the dad is whistling at the kid, and the kid is going to listen for the Doppler effect. So at which point, or for a change in frequency, let's see, who's blowing a whistle at A through E, will the child hear the highest frequency for the sound of the whistle? So the highest frequency is going to be heard when the child is moving fastest with respect to the sound waves. So if we think back to our experience with the pendulum, so at first I thought it was D because that's where the child is moving perpendicular, but that's really just the seat and not necessarily the ears of the child. The correct answer is C, because at point C, the child is moving fastest. So we spent a lot of time talking about simple harmonic motion and at equilibrium position. That's where the object is moving fastest. So because the child is moving fastest, the Doppler effect would be most pronounced, and the child would hear the highest frequency. Next up, do you expect an echo to return to you more quickly on a hot day or a cold day? So as temp increases, speed of sound That's a speed of sound increases as well. And if it's going faster, the echo would return to you more quickly. Question 2, sound waves are, so they're definitely not transverse waves, even though we draw them like this, remember? That's just a representation of regions of compression and rarefaction. Rarefaction? English was never my strong suit. So, definitely not transverse waves. We can cross that one out. Let's see, longitudinal waves. Hey, sounds good. Characterized by displacement of air molecules. Yeah, for sure. Longitudinal waves characterized by pressure differences. Those both sound good. So yes, the air molecules move back and forth, creating differences in pressure. Regions of high pressure and low pressure. Actually, it'd be like this, sorry. High pressure, low pressure, low pressure, etc. Okay. Yeah. 5. Musical note that is 2 octaves higher than a second note. So 2 octaves. We play A, 440 hertz. The next octave above is still going to be an A note, but it's going to be double the frequency. And we play another octave above, and it would be, can I multiply? It would be twice that. So we would have 4 times the frequency. A musical note is 2 octaves higher than a second note. A second note. So there we go, 4 times. Because we double and then double the double. 6. In which of the following is the wavelength of the lowest vibration mode the same as the length of the string or tube? So, lowest vibration mode, when we're talking about guitar strings, we can represent it like that. When we have a tube that is open on both ends, we represented it like this. So this is the fundamental resonant frequency. And when we had a tube that was closed, I'll do this to represent closed. Notice how I'm not writing all this stuff, but good thing you are. You wrote guitar, you wrote open both ends, and you write closed at one end. Good students. We represent it like this. So, the relationship between the length of the string or tube and the wavelength of wave. I'm hoping this makes sense. If not, you should ask me about it in class. Looks like this, and length is 1/4 the wavelength of the resonating frequency. So in none of these cases is the fundamental frequency, let's see, where are we? In none of these cases is the fundamental frequency, does the wavelength equal the length of the string or tube? Okay. And again, fundamental, that's the lowest frequency. And when we did that experiment and we listened to the speed, or we calculated the speed of sound in air, it's the fundamental frequency that we hear. When you pluck a guitar string, it's mostly this. There are overtones, but the one you hear most is the fundamental. 7. When a sound wave passes from air into water, what properties of the wave will change? So we talked about this previously, and in the last notes video, I think, where, let's see, what will change? So frequency is going to stay the same, but the wavelength and the speed are both going to change. Both wave speed and wavelength. The frequency does have to stay the same because it's kind of creating the waves. So it'd be something like fast, slow. Right, here's a division between two different mediums. So if we're passing from air into water, this would be like the air and the water, so the wave is going this way. And the fact that this is moving back and forth, it moves back and forth at the same rate. So frequency stays the same. Part 8. I think we're going to do a little calculating here. Guitar string vibrates at a frequency of 330 hertz. So I'm drawing this 330 hertz with wavelength of 1.4 meters. So that is 1.4 meters. The frequency and wavelength of this sound wave in air as it reaches our ears. So the string, boing, 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 moves back and forth, and that moves air molecules back and forth, and the sound waves reach out to our ear. Okay, so sound waves like this. And this question is asking about these, not this, frequency and wavelength of the sound wave in air, and they give us this 20 degrees Celsius, meaning we know that the speed of sound we can assume is 343 meters per second. Okay, so we want to know, we know that the frequency of the guitar string, because it's moving the air molecules, it's going to move them back and forth at the same rate. Now, how far they go, meaning the wavelength, that's another story. But our frequency is going to be the same. So, for sound in air, we know that the speed is 343 and the frequency is 330, so we can figure out the wavelength. Point of this question is the wavelength of the guitar string does not have to be the same as the wavelength of the sound wave in air. Excuse me. If we were to divide, we're going to get, I don't know, let's see, 10, something, 1 point less than that. This is my guess. I didn't calculate this beforehand, but it's something a little more than 1. It's definitely not 1.4 meters. So, aha, they tried to trick us, but I think it's going to have same frequency, yet shorter wavelength, even if I was a little off on there. Who knows? But part E sounds good. Oh, good, another video. Let's see. 9. Guitar player shortens the length of the guitar's vibrating string by pressing the string down onto a fret. So we had a previous question, right? Bridge, guitar strings, the neck, the tuner thingies, whatever they are. You can tell I'm quite the musician. And notice how they're getting closer together as we move in. Okay, so I'm sorry, what does it ask? The guitar then emits a higher pitched note because, so you pluck a string, boing, and then you put your finger down here and you pluck a string, boing. The tension has not changed. Tuning it changes the tension, but not putting your finger on one of the frets. The string can vibrate with a much larger amplitude. That would be related to how much you pluck. Just a little boing or a big boing. C, string vibrates at a higher frequency. Yeah, that sounds good. 10. Organ pipe with fundamental frequency F is open at both ends. And so you're probably thinking, hopefully thinking and drawing. Okay, open at both ends. We know the fundamental frequency. All right. If one end is closed off, aha, then you're like, hey, I know this. Closed. We did this. All right. The fundamental frequency will, so what happens to the frequency? This is some frequency F, and we know, what was it? The length of the column was half of a wavelength, and then over here, length of a column is fourth of a wavelength. So if this wavelength is longer, bigger wavelength, it means it has to have a smaller or lower frequency. So lower, the wavelength increases, the frequency decreases. So it would drop by half. This organ pipe would have a wavelength that is twice this. So a frequency that is half. 11. 2 loudspeakers. So this is cool. 2 loudspeakers are 10 meters apart in front of a large classroom. If either speaker plays a pure tone at a single frequency, 440 Hz, loudness seems pretty even as you wander around the room and gradually decreases in volume. Alright, so 1 speaker. But if we play 2 speakers, what will you hear? So before we answer, let's take a look at this. And I managed to turn the volume off on the iPad so it won't have that weird feedback thing in the previous, for the Morgan Freeman. Sorry about that. Let's watch.
The aim is to demonstrate that sound is a wave.
The apparatus is two speakers connected to a signal generator.
The two speakers act as coherent sources. Coherent sources emit waves that are in phase and have the same
Notice how
frequency.
they're wearing uniforms. Good thing
Waves from coherent sources form an interference pattern. An interference pattern is made up of a series of nodes and antinodes.
A node is a point of minimum vibration. An antinode is a point of maximum vibration.
Due to the interference pattern, the volume will increase and decrease.
So as they're going to play these, listen. Oh, and the nodes and antinodes.
Because it exhibits interference, this means sound is a wave.